David is a fellow at MIT Lincoln Lab, a laboratory fellow at Lincoln Lab, which is our big sister lab. At least that's how I think of it. David also teaches multiple courses at MIT on AI and system engineering and system architecture and large language models. So really great work, sort of famous in the circles of, I would say, FFRDCs and national security and technology. So I think we're really lucky to have David join us today. He's also the author of a super cool book, which David, I have my own copy here.
Oh, good.
I'll have to bring it to Lincoln Lab next time so I can get it signed.
Yeah,
But
sure.
artificial intelligence, a systems approach for architecture principles to deployment. So David, thanks again for being here. Really looking forward to your talk.
Okay, thank you for inviting me. And hello, everyone. Since you mentioned the book, I always want to point out that one of my greatest satisfaction now is due to a family situation that came down with cancer. She's fine now, but one of family members came down with cancer and she's fine now. I have decided to donate all the proceeds from the royalties of the book towards our early cancer detection at MIT. And I was just amazed how much we're lacking the use of tools and techniques like AI in the early detection of cancer. So it's great hope that my little contribution there will help in that domain. Well, thanks everyone for joining this morning. The topic consistent with your study is on AI systems engineering from architectural principles to deployment. And obviously in a 45 minutes talk, I'm only going to give you highlights of this topic here, but I think it'd be enough that it'll inform some of the objectives that you have for your study. So I'll begin in order to level the field from the perspective of terminologies. I'll start with a definition that I use on AI systems engineering, and then I'll focus on architecture. Because of the great interest on generative AI, I will address traditional AI, and then I'll follow that with generative AI, and I'll explain why I want to distinctively highlight those two as key elements of progression in artificial intelligence. And then I'll leave you with some future thoughts and recommendations going forward. So the definition that I have adopted in terms of systems engineering, it's shown here, and as all of you are very familiar with, the INCOSE, the International Council of Systems Engineering, is the place as far as systems engineering is concerned. And it's a discipline that has been in place for many, many decades. Unfortunately, the circles that I revolved in, and I'm sure Matt and others do too, that intersection of AI and systems engineering is lacking. And I have been extremely fortunate at Lincoln Labs to work on very complex systems. And I am completely of the opinion that we need more systems engineering in the development of AI to more effectively transition from development to deployment. In this definition, which I won't read it to you, since you can probably read it faster, I'm sure, than I can do justice by reading every single word here, I just want to highlight two pieces that I like right out of the definition, and that is the importance of tying technologies, processes, and people, and that's exactly what I'm going to address on this talk. The other element that I added to the definition is what my co-author and I in our book going by the name of FAST steps, which is basically responsible AI. And more and more, there's a great need to attend to things like fairness, accountability, safety, transparency, ethics, privacy, and security. And those are important principles. And I'm going to show you a framework that we used. And we conceptualized to cement these concepts. So the systems architecture, again, and many of you in this call, if not all of you, are of the same mind as I speak about systems architecture, because any complex system that I've developed, I've never been involved in it by just looking at one particular algorithm or one particular technology. I'm enjoying Lincoln Laboratory to implement space-time adaptive signal processing, but very quickly I realized that if we're developing a complex system, I better be more cognizant about the overall purpose. Why are we building what we're building? Which to me, that's the system architecture. So we formulated the systems architecture. It actually dates back to a study I ran, similar to what you're doing now, but focusing on where are the opportunities on AI. And again, similarly, I wanted to center that study on a systems architecture. So briefly, let me walk you from the left to the right. Of course, we need input data like from sensors. Most of the data that you see today is unstructured data coming from sources, especially in the advent of generative AI. But none of these data that we typically see either from sensors and or sources like notebooks or PowerPoint charts or Word documents, so forth, unstructured data. None of that is ready to go into machine learning algorithm. You got to condition the data. You got to do making sure that misinformation is attended to. I reduce the misinformation, biases, simple things like the dynamic range. I mean, if you take data that has a very large dynamic range, you need to make sure you scale it before it goes into the machine learning. If you don't do that, then the machine learning will be biased towards large numbers. All those kinds of things that you're all very familiar with. We call that data conditioning. Other people call it data exploration and so forth. That's fine. So data to information. And I will use the example of, just to keep it in this level of forum, I use the sample of the medical community. Let's assume a patient comes in and is being identified if that person has cancer or not, a cancerous cell. Data conditioning is taking MRIs, taking X-rays, taking CAT scans, and so forth, and then conditioning the data to make sure it's properly cleaned up, so that then it can go into a machine learning technique such as computer CNN, like the computer vision neural networks. And then the machine learning then is used to extract that knowledge. Yes, that person might have cancers in this particular part of the lungs or other parts of the body. And then it gets passed on to, say, a radiologist, which is that human machine teaming, the right-hand side of this chart. I put that as a spectrum because that part of it is often not seen and evaluated carefully to determine the trade-off between the confidence that one has in the output of the machine learning stage to the courses of action. In the case of the medical community, people can die if they say false negative is very large. False negative meaning identifying that that person does not have cancer. And then it's passed on to the surgeon, for example, on the right-hand side. Many of us in this call are involved with other applications, military intelligence, and so forth. Similarly, very, very significant courses of actions as well. So you got to take it as a trade-off. All of these rides under the substrate of modern computing, and the dominant parts of that are graphics processing units, for example, the ones from NVIDIA, or the tensor processing units, the ones from Google, for example. However, we can't properly design, develop, and deploy AI unless we seriously take a look at robust and responsible AI. And I put some indicators here. And of course, the Software Engineering Institute is a key iconic institution when it comes down to software approaches, software engineering approaches, verification, validation, security. You have a very large cert component that is critically important. How do you bring those elements into building complex systems? It's very well matched to the way going forward. No time in my career have I had a need to recognize how important it is, the right-hand side of these, that the technologies can inform policymakers, and policymakers can be better making policies that are informed by the capabilities of technologies. So this is the systems architecture holistically end to end. I'm going to just give you some highlights through the course of this morning. As all of you know, there are 4 key elements that you have to attend to when you're implementing machine learning techniques, regardless of what they are. I use the left and right. The left side of this chart is less appropriate for this audience, but in general, I use the left side of the chart, the ovals, because oftentimes people mix machine learning with artificial intelligence. Machine learning are the algorithms, it's a superset, but artificial intelligence is the end-to-end implementation of data, algorithm, computing, human machine teaming, all of those put together. But what do you need to implement the machine learning solution? Obviously, you need to define what problem are you trying to solve. And that's why I want to speak about traditional AI and generative AI, because I find that in many conversations, everybody thinks of, the answer to everything is generative AI. And I'm here to tell you that's far from the truth. Generative AI, even though I use it both professionally and personally, and I think that is the future, we cannot ignore traditional AI because generative AI is based on what's available in the internet. Traditional AI to me is things that you get from sensor, for example. And I'll explain a little more about it. And I come from a sensor background, so I sort of I have a tendency to make sure people don't ignore traditional AI. So you got to define the problem, gather the respective data that is needed. You got to train it properly with the right data. And then, of course, you need the computing. So those are the key elements. And I'm just going through a little bit of background here to set the stage for the remaining charts. As part of the study we did, and also I teach this in the class that I teach, there's another important aspect here that needs to be addressed. And please stop me at any time. Actually, when I get to the outlines, I'll ask if anybody has any questions or comments. But one of the things that came out of our study, and then I continue to progress in this when I teach my classes, is that we're a lot of what this chart is illustrating. The vertical axis is a notional impact, and the horizontal axis is time frame, obviously also notional. But I think there's a lot we can do today in terms of what I call Horizon 1, content-based insight. Why I think we can do a lot today in this area is because we're yet to truly effectively combine multimodalities like video, like audio, like images, like, of course, text. So you see, we need to reduce the user workload, but more effectively, just like we humans, we use my hands, but the eyes, the ears, and so forth. The other element of it, and the way you read these, what should we be investing today so that they'll be available in 1 or 2 years from now? The middle one, Horizon 2, is what should we be investing? That's sort of the horizons. And what should we be investing today? So say into 3 to 4 years, we should be more effective at enriching insight. And that to me is the collaborative work between humans and machines. And when I mean by humans and machines, I don't mean talking to a chatbot. Of course, that's a human-machine interaction, but I think of it much bigger than that. Why can't we have machines that are collaborating with us as truly part of a team? So they're not just used as tools; they're part of a constructive, integrated, collaborative work. And we're still a long ways from getting to that vision. And ultimately, context. I think context is extremely hard. You probably see a reflection from my glasses because I'm in a location here where I'm close to my router, but I'm also close to a window here, so I get a lot of reflection. When I look outside and I see, oh, it's sunny, I immediately can tell you that it must not be raining. Try a computer to go do that. Well, you got to have sensors that go look and see what the conditions are. You got to also probably read about the weather and so on. And then you got to aggregate that. So context is very hard. Even Google Maps has a hard time doing those sorts of things. So let me play a video for you. And please stop me if you can't hear it, but let me play a video for you.
A driver trying to get to DIA hit traffic this weekend. No surprise there. So she tried a detour recommended by Google Maps. Here's 9 News reporter Jordan Chavez with what happened.
Head southeast.
Many of us rely on a voice like this
In a quarter mile.
to help get around traffic like this. Some days it works. On others, like this past weekend, it doesn't.
Right, it was crazy. Yeah.
Connie Monsees was on her way to Denver International Airport to pick up her husband Sunday morning. With just a little more than 5 miles to go, she says traffic stopped.
So I pulled up my phone and went to Google Maps to see if there was a detour. It told me 47 minutes if I stayed on Pena, 23 if I took the detour.
While the latter choice seemed more appealing at first, it quickly became the slower option when the paved road turned to dirt not far from Tower Road in 64th.
It was like we were out in this farmer's field and there was just 2 tracks where he had driven across the field.
Connie wasn't alone.
No, there was like 100 cars out there.
And she says the rain over the weekend didn't help. Pictures she took show cars stuck along the muddy road.
And this gentleman stopped at my car and said, "Are you going to the airport?" And I said, "I am. I have to pick up my husband." And he said, "Can I throw my bag in your car?" His sister's car was not going to make it, and so he hopped in.
A second person hopped in with Connie, and all 3 eventually made it to the airport. Connie says she'll still use Google Maps,
Use the right 2 lanes.
but combine this voice with the smarter one in her head.
Yeah, and it's many of the efforts that are going on more at the research side, things that you see at the Association for the Advancement of AI, AAAI, which I'm heavily involved with in terms of having started a workshop years back on AI for cybersecurity. Of course, NeuroIPS, all of you are familiar with it, and other venues. It's that combination of neurosymbolic. Neural networks are more about the system one, the fast thinking, as Nobel Prize winner have said, Danny Kahneman, fast thinking system one. System two is more of the things that we have to reason about it, and how to combine those. That's an area that I'm looking forward to seeing that there's great breakthroughs. It's still more at the research stage. So before I get into the next stage of my discussion here, any questions before we discuss traditional AI? Give you some highlights. Again, on the short time frame here, only doing highlights. No
David, I'll ask one question on your horizons slide, from content to collaboration to context. What are your thoughts on the current movement towards agentic AI, which is, a technology coming back around again, like many of these things, but there's a lot of
Sure.
excitement around what's possible with agents and building human AI teams
Right.
and those sorts of things.
Yeah, okay. Let me give you a quick answer and then we'll cover that. I have that covered under generative AI. My thinking on the agentic AI, and I'm glad you asked, because that's an example where we can bring context. In fact, when you're developing the large language models, you have something called context window. And that context window includes what happens to a given word that is predicted based on what's happened before. And that's one of those examples where context there, the bank, well, by doing symbolic, by doing the similarity and by doing the right embeddings, you can then understand, depending on what's in that context of the sentence, what is that bank? Is that the river bank or is that a financial bank? That is absolutely context. But that's that's limited to, for example, large language model. When you're dealing with a much broader subject area of the application of AI, for example, like that like that video on the driver using Google Maps, where you're taking sensors and you're taking all the type of information, context is a lot harder. So great question. And yes, context, we're getting there much faster. And once you bring agentic AI, which I'm going to talk about later in the generative AI portion of this talk, I will address that in more detail. All right, real quick, just clicking my phone here to make sure I don't fall behind. I just want to highlight that when I refer to traditional AI, I'm not talking about artificial general intelligence. Great research there in AGI, but I find it hard to spend a lot of time as an application AI practitioner on AGI. I'm more interested on how can we use what's available today to solve real problems. And that is in the category of augmenting human intelligence, which is the operative word in the definition. The other thing I want to highlight with this chart is that the algorithms have been around for quite a while. The convolutional neural network that Ian LeCun from New York University and also Meta, he did great research back in '89 on the right-hand side of these. It was not until the advent of Professor Fei-Fei Li, now at Stanford, prior to that she was at Princeton, that really brought up the ability of data. And that with computation is what led, for example, to this row here on the 2014 GoogleNet object classification at near human performance. The one right before that, 2012, was the AlexNet. But same, so the main takeaway from these, the algorithms are shown here on the right-hand side have been around for a long time. It's the advent of the data and the advent of the computation. Here's a taxonomy of the different classes of algorithms, techniques, supervised learning, unsupervised learning, reinforcement learning. I'm just going to give you one example from some of the researchers that used to work for me and at Lincoln Labs, and it's fascinating because it crystallizes very clearly the value of neural networks, which I highlighted here in red on your left-hand side. So here's an example that Barkstrom, Bernstein, and Robert Dunn did, and clearly shows the value of these. It shows two things. One is that you need an immense amount of data, 500 plus hours. And two, this is an example where deep neural network can do pattern matching very nicely. For example, non-stationary noise. In this case, non-stationary noise is the sound of a siren. So the way you read the right-hand side here is that the deep neural network can extract out the particular noise and then mask it out of the input, not corrupted, but the input noisy speech, and get a much clearer output. So let's listen to how it progresses from a noisy speech to a much clearer speech.
They all agree that the essay is barely intelligible.
That's the noise, a siren.
They all agree that the
barely
essay
hear it.
is barely intelligible.
But it's much clearer. So that's an example of the power. And there are many other examples that one can see. However, in all of these, as I emphasize on the human-machine teaming, what I wish we would pay a lot more emphasis on is how do you measure the output? They are great, and I go through that in my courses. They're great measures of performance, like accuracy, recall, precision, F-score, and so forth. Area under the curve, confusion matrix, and all that. But I'm interested as a AI practitioner, especially coming from a systems side, systems engineering side. What's ultimately the measure of effectiveness? The confidence in the machine making a decision to the consequence of action. If, for example, in the medical application, I use the medical application, repeating that as the proxy for many of the cases where consequence of actions does matter. If the FN, the false negatives are very large, then that can have a huge impact on consequence of action. The person can die. And medical application, most applications are here in the middle, machine augmenting humans. So let me move out now to generative AI. So everything I talked about in traditional AI is using, for example, machine learning, which with like supervised learning, where you're passing in a speech to recognize the output, or clean up the output, or you're passing in sensor data, for example, on driverless cars, where you're using radars and lidars and so forth to determine if a pedestrian is crossing the street, like it happened in Tempe, Arizona, which unfortunately the Uber driver hit the person and the person got killed. That's all traditional AI, and that needs a lot more work. And I want to emphasize that many of those cases require careful attention. It's not all about generative AI or generating things. But any questions so far? If not, we'll move on to the next stage. All right. So generative AI. So my great friend Joe Campbell, he put together this chart, and I really liked it because I like simple thinking as we're trying to set the stage, and then we can get into the detail. He breaks it up very nicely. I worked on handcrafted, there were knowledge expert system. My first day involvement in AI dates back to the late 1980s. But this is also not a notion of the impact relative to time. And as Matt just pointed out about agentic AI, which I'm going to discuss in a few minutes. So far, I just gave you highlights of one example of deep neural networks. Now I'm going to focus on these two here on this chart. So for setting the stage, I also want to emphasize that generative AI is not new per se. The advent of the 2017 paper by Google was phenomenal. Attention is all you need. But what's underneath the hood leverages unsupervised learning, supervised learning, and reinforcement learning. All of you know that are involved with large language model. There is a step in the last stages of the design of a large language model called reinforcement learning from human feedback. That's the very reinforcement learning that deals with establishing a policy, establishing a reward, and then leading to an action. So therefore, you can see these four classes here with generative AI. It's leverage much of the many decades of great work that is done across the world on all of these. I'll give you a couple of examples. Unsupervised learning, for example, one of our senior staffs at Lincoln Lab came up with an approach to characterize malware in the web proxies by integrating and bringing a lot of that information and doing PCA, principal component analysis, to highlight that part of that large web proxy of IP addresses and identify a malicious IP. And then follow that with k-mean clustering to then zero it in even more. So those are examples where there's tremendous value. And think of all of these on the left-hand side of generative AI. Think of all of these as traditional AI. And that's a real nice chart that Bob Bond, also from Lincoln, has put together. A great thinker in this area. So a quick definition, it's kind of wordy here, but one of the definitions that I like to use is this one here. And again, I'm not going to read all these details, only to point out that generative AI, just like the word implies, is generating information for the user. So when people talk, including me, when we talk about, one of the deficiencies of generative AI is hallucination. Well, let's remember that by its design, generative AI is designed to create content for you. So therefore, hallucination tends to be a byproduct, and therefore you need to pay a lot of attention to make sure that one attends to the issue of hallucination. So the main takeaway from this lengthy definition is generative AI includes text, images, videos, code, and synthetic data. Many people are starting to use generative AI because it generates content to create synthetic data then can be used for the application of other AI approaches. And ultimately, just as Matt asked just a few minutes ago, is, for example, with agentic AI, the ultimate goal is to increase organizations' productivity. So we put together this AI stack, and I decided for generative AI, in one of the classes I teach on large language model, I use this architecture, which is a simplified version of the one I showed you earlier. I use this one on purpose. And the reason I use it is because there are very specific things that we need to attend to. We're very excited. My background is signal processing from school. So I love to work on AI models. I would love the algorithm side, but there's a lot more, especially when you're thinking at that intersection of AI and systems engineering than just the models themselves. And the models will continue to evolve very quickly. I was teaching my class in January, and DeepSeek was announced. So the models will continue to be advancing very quickly. OpenAI just announced a few other new advances, particularly in creating images using DALL-E. So my strong recommendation to all of you in your study is pay attention to not only what's underneath the model, like the infrastructure, like the data, and also up here in terms of the operations layer, in other words, the interconnectivity among all of the pieces working together. And these systems are very vulnerable to adversarial AI. So we need to attend to that. And of course, security. And that's why I put security here all around this area, because security ought to be incorporated from the very beginning of the design cycle. I also have on the right-hand side, what's going to be the implication on the skill force? I'm paying much more attention to the workforce. Why? Because this would have generative AI is going to have absolutely an impact on the workforce, no matter what particular discipline you're involved in. We need to be cognizant that we need an AI governance. More and more organizations are establishing that at the board level and also at the C-suite level. But there are also other skill sets like AI systems engineering and the complex systems that I have been fortunate to work on at MIT Lincoln Laboratory. The system architect was always a key person in anything that we developed, and the associated systems engineer that thinks about the overall end-to-end system. Also, let's not think of the CIO or the IT offices as not being a critical part, but they're absolutely a critical part of a complex system because they enable the infrastructure for those designing the algorithms and for those implementing the overall system. I won't spend a lot of time on the chart. I want to make sure I get done on time. But this is a nice depiction of where generative AI works well. Of course, it works well with generating content, chatbot, knowledge discovery. One of the AI practitioners that I invited to one of my courses, Jim McMillan, he leads the AI at Morgan Stanley, and he said he's using generative AI to help the advisors, not the clients, but the advisors more quickly discover information as they advise their clients. But I really like this chart because non-generative, like machine learning, a lot of applications here. And I think many of these as a result of applications where you're using sensor technology. All right, so agentic AI. Yes, that would have a tremendous implication. Agentic AI are systems that can plan, they can reason, they can plan, they can take actions and so forth. Some of the properties is that they can work together, and they can also be, although we haven't seen many of them yet that way, but ultimately you'll be able to communicate with the agents using natural language processing and so forth. So I put together kind of a topology, but I really wanted to show you these for two reasons. One is that agents in this context, as shown in this definition, agents in this context are, for example, let's take the example like I used earlier, the weather, and in finding the best restaurants in Boston and finding the distance from MIT Cambridge, located in Cambridge, then an agent could access the weather API. An agent can then determine, based on the output of that, what are the best rated restaurants for seafood, and also based on the distance will determine what output based on a prompt here where the user says, give me, based on the weather for tomorrow, the best restaurant, seafood restaurant close by to Cambridge. Of course, it's got to go through a reasoning, a thinking, and assisting and giving a response. But I also overlaid on it what we are all very familiar with, given our backgrounds, the OODA loop, which is observe, orient, decide, and act, which fits very nicely with this agentic workflow. Agents are going to be here to stay, and they're going to have a dramatic impact on everything we do. I encourage some of you. I was catching up with some of my reading this morning. Great article by the CEO of Salesforce talking about in the Wall Street Journal, talking about the value of agentic AI, for example, in Salesforce. But here is a simple example where to use agents. Answering a user prompt depends on the output of other tasks. Accurate prompting response will require accessing multiple tools, like I just show you this example on the right-hand side of the weather, the restaurant with the highest rating, and so forth. Taking action, and agents must access different external tools to work together in their response. Let me quickly play these because of you'll, given the powerhouse that you all are from, Software Engineering Institute. Here is Andrew Ong speaking about the value of agents when you're designing code.
That gives coding puzzles like this. You're given a non-empty list of integers, return the sum, and that turns out to be the solution. And it turns out that GPT 3.5 on the evaluation metric, parsec K, got it 48% right with zero-shot prompting it to just write out the code. GPT-4 does way better, 60%, 67% accurate. But it turns out that if you take GPT 3.5 and wrap it in the agentic workflow, it does much better. And so, and with GPT-4, that does also very well. And so to me, one thing I hope you take away from this is, while there was a huge improvement from GPT 3.5 to GPT-4, that improvement is actually dwarfed by the improvement from GPT 3.5 with an agentic workflow. And to all of you building applications, I think that this maybe suggests how much promise an agentic workflow has.
All right, any questions? And of course, I'll leave time at the end for additional questions. But before we wrap it up with the way forward and recommendations. Oh, okay. So let me,
David, I think there's actually one question from
okay,
Tom.
Go ahead, please. Go ahead, please. Go ahead.
Yes, thank you. On the agentic aspect, I know a lot of researchers right now are discussing when agents are interacting with one another and they are serving as representatives. One of the challenges to determine is verification and certification. That how do I know that the agents that I'm interacting with are representing the other agents or possibly the other humans in a system? Have you sort of any recommendations or thoughts on where people should be looking in terms of that conversation of authentication and verification of agents as we move into that space?
Yeah, no, I think that's lacking. And I think that's highly needed because of the vulnerabilities of these, the brain behind any agent obviously is the XLM. It could be visual large models or large language models and so forth. And we have a lot of vulnerabilities of those individually, let alone as they're working together. And I think that's an area of need in terms of the research side of it, and research side when it comes down to verifying this capability. Just like SCI has great iconic contribution in these areas. Verification that the software pieces and the hardware pieces requiring hardware computing are working together, but then validating them. How do you put all these pieces together? So I don't have any solution for that. I think it's in the problem space, absolutely in the problem space. So great question. So here are some highlights on when you're thinking at the systems level. You got to worry about not only formulating an overall strategic roadmap, a blueprint. We live by these at the work we do when we're putting complex systems. What's the overall plan? What's the overall blueprint strategically? But I want to emphasize the customer. That should come at the very beginning, and do things like agile development environment, scrums, and so forth, the minimum viable product to attend to those sorts of things. And there are others that's outlined here that I'll highlight in the next several charts. So we put together this AI ecosystem, and there's several things that I want to highlight here that I will leave you with. And that is that bring the customer from the very beginning. Even though the user and customers are here at the end, they got to be all the way from the very beginning. And of course, the ultimate recipients of these at the end. But another important takeaway, there are many takeaways from these, so I'm just going to give you highlights, is make sure that your operational environment, make sure that your prototyping environment is consistent with your operational environment. That's where you run into these chasm, or the classical Gartner's curve of being excited about the development and then going into the value of death because it cannot get transition. Why? Because your operational environment has certain APIs, certain computing environments, certain interconnects, certain type of interfaces that they need to be captured in your prototype. I don't mean identically, because the systems on the right here, operational, can be very complex, but at least they need to be representative of where you're going to deploy. That's another second takeaway. Third takeaway from these is gold standards. And that's systems engineering thinking. I've done it. I mean, in the systems that we've developed, we've always had the gold standards to, if something went wrong with the system, we can always go back to our gold standards and do critical system analysis on what you expect out of it. And we can discuss it more if you like in the Q&A. I also wanted to address the responsible AI, and we divided into the problem space, the solution space, and notice that it's ... here, because in one chart I cannot do proper treatment to the overall topic here. But there are a lot of issues in the problem space, both with traditional AI and generative AI. Hallucination we talked about. I'm going to have a chart here next on social technical issues as one example. But there are many others: deep fake, evasion attack, poisoning attacks, jailbreaking, and so forth. Unfortunately, there are efforts ongoing in many organizations across the AI community where people are advancing some of these capabilities. Red teaming to me is critical. And we come from, and you do too, we come from putting red teaming, for example, for cyber, even before that for other applications. And that needs to be overlaid on a governance structure above that. So social technical, there's not only individual issues, there are also societal issues much globally. But please remember that each one of us has a responsibility individually to also be concerned about the implication on the organization. We can make errors in the development of AI capabilities, and that not only would have implications on us personally as professionals, but also your own organization in terms of many different things, including the consequence of the reputation of the organization. I won't read these because it's too wordy and too lengthy. But I'd like to just highlight a few things. There are critically important questions that need to be asked when you bring the stakeholder from the very beginning. And that is, what problem are we trying to address? So that would then lead to what kind of solutions. There are solutions, machine learning solutions in AI that are a lot simpler to implement, support vector machine, logistic regressions, and so forth. So let's understand that. What kind of data do we need? responsible AI, and just the question that was just asked about evaluation and ultimately the deployment. So we put forward, and it's described in the book, a set of system readiness levels. It's a little bit of a take from the NASA technical readiness level, but when I think of technology readiness level, in the description that are under the TRLs are more about the boards, how do they come together and so forth. For this purpose, I'm interested at the systems level. What are the business goals? What are the stakeholder requirements? And so on, marching all the way to the minimum viable product. And then ultimately, how do you implement it in a flow that includes continuous integration, continuous delivery, as referred to as SRL 9. And then I highlight a number of common pitfalls that pretty much are consistent with the SRLs and provide some recommendation. Some of the pitfalls is not understanding the key business needs, and therefore that's where the strategic roadmap plays a key role. And we have put forward, describing chapter 9 of the book, AI strategic development roadmap. Things like having well understood not only your development environment, as I show you in the AI ecosystem, but your deployment environment. And also make sure that you're not focusing on just a monolithic solution. There are great tools out there, microservice, containerization using Docker, Kubernetes, and so forth. Other approaches are like that minimal viable product MVP, I would call it minimal viable product and service. It's not just hardware things, but also software. And then the inability to also take into account a highly constrained environment. I feel that that's a very important area. Several of the systems that I've been involved in needed to work in very highly constrained environments. So we need to worry about things that reside at the enterprise level versus things that reside at the edge, where SWOT and cost are very critical. And a couple more. Disregard of the environmental social governance. Well, the environmental is a big deal regarding these large language models. You need to attend to that. Also put guardrails that would help you to make sure that you're attending to that responsible AI. And the last one here is leadership and talent, which leads me to the next one. So far, I've talked about technologies, process. Let me finish up with the people side. So I love these 7 takeaways from the National Academy of Engineering. And it's a very prestigious organization. They're looking at the engineer of the 2020 century, to be creative, to be a good communicator. But here's what caught my attention, a couple of these. Business and management acumen. Our talented people, regardless of where they are in their career, have to understand, and that's where systems engineering come in. What problem are we trying to solve? Where's the business need? What are the stakeholder requirements? Ethical standards, professionalism, be agile, being able to quickly adapt to the needs of what you're developing, especially in AI, where things are moving very quickly, and lifelong learners. I'll leave you with a set of recommendations, both from a systems engineering perspective, as well as the workforce of the future. Let me pick one here. Digital natives will expect AI tools in their work environment. So I continue to stress the importance to recognize that as the workforce continues to evolve in this AI domain, they're going to be so comfortable, i.e. digital natives, with AI tools that we better be positioned in any organization to provide them those tools. However, let's make sure we don't neglect the systems engineering aspect of how do we wrap this together so we develop capable systems. And I believe very strongly that systems engineering will continue to be an important discipline. And AI is a tool that will impact the workforce. So that brings me to the end. A AI system architecture framework establishes the key building blocks necessary to develop and deploy operational capabilities. And again, I'm focusing on from development all the way to deployment. Traditional AI will continue to augment human intelligence, particularly when it's driven by sensor data, for example. generative AI will increase the productivity. And let me emphasize here, since there might be some people in the audience that are more in the business operation, I think that low-hanging fruit is in the business operation using a generative AI. Why? Because it can help with better connectivity between the contracting, finances, HR, human resources, and so forth. But you got to have a digitally transformed environment where there wouldn't be silos, and they nicely can communicate among it and communicate digitally. Is what I mean. Multiple surveys highlight that the biggest impediment are recognizing where the value of AI is versus hype and the lack of talent. So with that, we come to the end, and hopefully still some time for, I was trying to finish around 10:45, so in a little bit over 5 minutes more. I see the people's hands here. So Matt, you can tell me, or I can pick Marisa and others. Go ahead, Marisa.
Yes, thank you. I was wondering how you view the changes in data conditioning and requirements for data preparation in the age of generative AI, where the data sets are larger and coming from these less defined sources.
Yeah. Yes. Yeah, that's a very, very, very good question. That's the advantage there is that, so there's a good and a bad situation there. You're right that it's hard to treat it as, for example, sensor data, which is much more defined. In the case of generative AI, I'm thinking of large language model, the amount of data and the amount of token is so large. However, so yes, that's a vulnerability. However, the great benefit of the architecture of, for example, the decoders is that ultimately at the end, it's all statistically based. So by having, it's all based on, if you go from logits through softmax, and then you pick the one with, or the computer, the algorithm, the architecture picks the one with the largest probability. That with that, which is unsupervised learning, followed by supervised learning, where you have well-defined set of documents that you're using in the training, followed by reinforcement learning from human feedback, that has strengthened the output of large language models to be more reliable. So yes, you're right. You start with an immense amount of tokens in the billions, but at the end, through all this rigorous process in between, you can end up with a sensible output, as we know. But having said all that, you still need to make sure that as a human, you have red teams and others evaluating the output. But great question.
Thank you.
Okay. Go ahead.
Amy?
Yeah, so I had a question. First of all, I love this presentation. It sings to my soul quite personally. So this is great. I did wonder though, are there any concepts, that you shared today that you sometimes get pushback on, or that people are like, "Oh, Dave, what are you smoking?" And if so, how do you handle that?
I'm trying to think if in that case of the pushback, trying to see if there's a trying to see if I can think of any particular instances that are tangible that I can give you as a feedback. I can't think right on my feet here of any direct pushback. It's more about the how. For example, I get questions asked on the human-machine teaming. How do we get a better handle on how to deal with that? Because it's tough. It depends on the application. I use the medical application as a proxy, but it depends on the application. The other one that it's in the area of robust and responsible AI. And in robust, it's more about security. How do we put our hands around the security aspect of it? Because the systems, as you know, they're so vulnerable. So it's more about the how. How do we and it's yourselves, other FFRDCs and other places are working hard on the solution space. The problem space can go forever. I have dot there, can go forever. But the solution space needs a lot more. But I haven't had any. I guess the only one that I'm glad now you asked. One that I want to clarify: when I have sources, I have sensors there, and audio, for example, is more of an unstructured data. But if the sources also have metadata, that's why I put it under structured data. So sometimes I got to clarify in the overall architecture. But I really haven't had a case where there is any argument about the flow and the end-to-end architecture.
Awesome.
It's more about the how of the individual building blocks. People are very comfortable on the how for the machine learning box. And then computing is pretty well understood as well. But the other pieces that are also critical to putting an end-to-end system together, HMT, human machine teaming, robust, responsible AI, and so forth, is still a lot to be done there. And of course, the CDAO office at SEI is heavily involved with the chief of data AI office. They're working on some of those topics like responsible AI frameworks and so forth. NIST, for example, has a lot of advancements in those areas of creating approaches, standards, and techniques. But it's a lot of work that's still in front of us. If I may elaborate a little more, if I may, another thing I want to leave you with is The Economist have a great terminology, not just in the AI domain, but they got great terminology that have been used throughout history called general purpose technologies. AI is a general purpose technology, such was the the mobile phones, the internet, and so forth. And the comment they make, like Daron Acemoglu, who just won the Nobel Prize, another person of that class is Eric Brown Johnson from Stanford, Darren Acemoglu from MIT, got the Nobel Prize. He said, we haven't even seen the beginning of the impact because ecosystems have got to be established as some of these general purpose technologies evolved. And in my opinion, they're absolutely right, because we didn't really see the advent of the internet until that ecosystem got to be evolved decades later. But I think in AI, it's going to accelerate much quicker. And that's why the studies like you're doing is so timely. So I just wanted to add that too, because it's something that we tend to, as that technologies, we tend to not pay too much attention to the economic side. It's a lot of economic issues that also need to be taken into account.
Well, Dave, we're at time. I actually have a question. I'll follow up an email on that question. But great talk. You covered a huge breadth of activity in AI and some history and some forward-looking things. A lot of insights that will help us with our study. So really appreciate you making the time for the talk. The interaction has been great.
My pleasure.
Thank you so much,
All
Dave.
Right. Thanks, everyone. Have a great weekend.
Take care.
Bye.